So on Friday we looked at what are called static condition or static Newton's second law problems where the object's not moving. Okay? In a static condition question, the object's not moving, the net force is 0. Okay. Could I also have a static condition question where the object was traveling at a constant velocity? Yes, because it's still static. The velocity is constant, not changing, so there's still no acceleration. So we got to watch for those two situations in any Newton's second law problem. It says the object is just, or the context says the object's not moving, or the question specifically states the object's moving at a constant velocity. We know then that the net force is 0 in both of those situations, so we've got to watch out for those. Another type of problem, and it's my favorite kind, make note of that, my favorite kind often ends up on unit exams, would be an inclined plane. All right, so the inclined plane is the simplest machine. Why? Well, it makes work easier. When we get to the work and energy part of this unit, okay, we'll talk about how pushing something up a ramp and lifting it to the top of the ramp is exactly the same amount of work. But you use less force if you push it up the ramp. Okay, it's a force multiplier. All right, if I can't lift something because it's too heavy for me, which of course is impossible, but let's say it is. Okay, it's too heavy and I can't lift it, I can use a ramp. I can move it up the ramp because I don't have to exert as much force. That's how the pyramids were built. Aliens did not help. Okay? Simple machines and many slaves is how these things were built. And very, very long ramps, right? That actually just wound around the pyramids. Okay? Just made out of, something they had lots of sand. Okay? Make a big, big ramp, right? And you can just pull these things up the ramp and you don't have to have magical aliens with force fields moving them to the top. All right, simple machine. It lets you move something uphill, okay, easily. All right, so we want to calculate the acceleration of the 10-kilogram box. So if I just put this 10-kilogram box on this incline, let's say the incline is frictionless, what's going to happen to it? Obviously, it's going to slide down the ramp. Okay, very clearly, it's going to slide down the ramp. Will it slide down the ramp at 9.81 meters per second squared? No. It will not. I mean, the last time I checked, if I get on a bike and point it down a hill, it's not like falling. Okay? I mean, I accelerate, make no mistake, you can pick up a lot of speed, but it's not the same as falling. All right? Even if the ramp is frictionless, it's still not the same as falling because there are a number of other forces that are involved. Okay? So this is what we need to know about an inclined plane. What pulls this thing down the plane? That's what everybody says, but I set you up. Okay? Gravity pulls which way? Straight down. It doesn't pull down the ramp. It pulls straight down. So that's one of the forces acting on the 10-kilogram mass. The force of gravity. But it's pulling it down, straight down. Now, what's preventing this thing from falling straight down? The ramp. Okay. Now, we talked a little bit about this force the other day, but we haven't talked a lot about it. And it's called the normal force. Okay? The normal force is that reactive force that's always there. So right now, for this depth, gravity is pulling it down into the floor. And the floor is pushing straight back up. A surface always exerts a normal force perpendicular to itself. All right? So there is a normal force as a result of the ramp that is pointing straight out from the ramp. Right here. Since the ramp is frictionless and there's nobody pulling this thing up or down the ramp, those are the only two forces involved. Now, is force a vector quantity? Okay, how do I add vectors? Tail to head. Okay, so I just put those two vectors tail to head. Look what their resultant is. Is it parallel to the ramp? That's why something goes down a ramp. The vector sum of those two forces points down the ramp. Gravity and the force of the ramp work together to produce this acceleration down the ramp. Okay? So always these two forces are involved. All right, so we got force of gravity going straight down, normal force going straight up, and then this force, which we call F parallel. So it's F with two parallel lines. It's the force parallel, or the component of gravity that is acting parallel to the plane. Right? When we're doing the sum of all forces in a question like this, that's essentially the net force. Okay? In a more complex question, I might have friction or somebody pulling the rope, pulling on a rope that's attached to the box. I'd have other forces. Okay? So this wouldn't end up being my net force. It would be part of it. Right? But in this case, this is kind of the simplest one. All right. So this angle here is 30 degrees. What do you suppose the angle is between these two forces? The same. Yeah, they would be offset by the same amount, right? I mean, if it was flat, gravity and normal force would be equal, right? They directly oppose each other. So if I start tilting the floor, okay, there's going to be that angle of tilt between them, 30 degrees. Since I know the mass of the box, can I calculate the force of gravity? Okay. All right, I have the hypotenuse and an angle, and I'm looking for the opposite side, F parallel. Can I find it? Sure can. This is always going to be true for every inclined plane you do. F parallel will always be the sine of theta times the force of gravity, because the force of gravity is always going to be the hypotenuse of that little triangle we just drew inside. Right, so for this question in particular, it's going to be the sine of 30 degrees times 98.1, which will be 49.05 newtons down the ramp. What are you trying to see, Sydney? Sydney, what are you trying to see? No? Okay. All right, so now I've calculated my net force. It's the vector sum of those two forces. Can I calculate the acceleration now? Okay. So my acceleration will be F net divided by m, 49.05 divided by 10, 4.91. Actually, we only have two significant digits here, so 4.9 meters per second squared down the ramp. Okay, so this triangle is the same for every inclined plane. Gravity is always the hypotenuse. Normal force, which we won't even use until we start covering friction, is going to be the adjacent side. Okay, F parallel will always be the opposite side, and this angle is always the same as the angle of incline. Okay, so if I have a 30-degree ramp, 30-degree incline, the object accelerates at half the rate it would if it fell. Okay, is that really fast? How steep is 30 degrees? We all go, well, it's like less than halfway up. It's not that bad. Guys, this hill out here, 32nd Street, at its steepest point might be about 8 degrees. Okay? If you're walking up it, it can seem pretty steep, but you don't build hills, especially for people to drive up, that are more than about 10 degrees at the most. Okay? Sometimes in the mountains you'll see those signs that say like 10% grade, okay, or 8% grade. That's 8% of 90. Okay, 8% of straight up in the air, and they seem really steep, but they're like 7 degrees, 9 degrees, the most maybe 11 degrees. Okay? They're not huge inclines, but they feel steep. Okay? A 30-degree incline is really steep. Okay. All right, so what we got to get out of this is that we've got an internal triangle that's part of every inclined plane that looks like this. Gravity is always our hypotenuse. Our parallel force, the one that's going to pull down the ramp, is going to be the opposite side, and normal force is going to be the adjacent side. Okay? All right, now I'm going to give you one that's an inclined plane, but it's a little bit, it's got other forces. Okay? These forces are still here, but it's going to have other forces. Not that bad. Okay, this one. I have a 340 Newton box. What did I just give you there? Nope. It's a force. Which force? That's its weight. What force is weight? Gravity. Okay? Always be on the lookout for this. In this unit, sometimes they'll give you, instead of the mass in kilograms, they'll give you the weight in newtons. So they just told me what Fg is. Okay? So I know what Fg is for this question. It's 340 newtons. Okay? So this box is being pushed up a 30-degree incline at a constant velocity of 1.5 meters per second. The applied force up the ramp is 200 newtons. What's the force of friction? So we're going to walk through this one together. This one's a bit more involved, okay? But I want to show you kind of how an involved one works. Okay. What forces are acting on the box right now? Right, okay, so we got gravity and normal force, right? Okay, so gravity acts this way, straight down, and they told us what that is, 340 newtons. Okay, normal force is this side, but I'm not going to need it for this question. It's just there, but I don't need it. Okay, and then I've got this side here, F parallel. And that angle there, that's 30 degrees. What other forces are acting on this box? All right, friction is acting on this box. Which way is friction acting in this question? The box is moving up the ramp, so friction's acting down. Friction's always opposite, okay? It's always holding you back. All right, so friction would be here, okay? What other force is acting this way? I may have already put it on the diagram. Force parallel, right? Right, force parallel is acting down the ramp, and what's acting up the ramp? An applied force. Okay. I know the applied force is 200 newtons. Okay, so I know the value of this. I'm being asked to calculate this. What else can I calculate right now? Nope, I can't calculate force normal, and I don't need it. I can calculate F parallel, right? I can calculate this side of the triangle because I have the angle, and I've got this, 340 newtons. Everybody with me there? Okay, so I'm going to calculate F parallel, same way I always do. Okay, it's the opposite side, so I'm going to take the sine of theta, in this case 30 degrees, and multiply it by the hypotenuse, which is gravity, 340. So F parallel is 170 newtons. That's why I always pick 30 degrees, because then it's easy to do in my head. Okay. All right, so now I know F parallel is 170 newtons. I'm being asked to calculate the force of friction. Now, I'm kind of stuck here in that I can't do vector sum of all forces yet because I don't have all the forces. Is there another way to calculate F net? Mass times acceleration. Okay, so what is the mass times the acceleration equal in this question? question again, I'll enunciate the part that's really, really important. 340 Newton box is being pushed up a 30-degree incline at a constant velocity. What's the acceleration in this question? Okay, what's the net force in this question? Ah, okay. So F net equals 0 newtons. Alright, so I now know the sum of all forces, right? That means the forces up the ramp and the forces down the ramp are what? They're equal. Yeah. Okay, that's an important thing to realize in this question. In fact, if you don't realize that, you will never finish this question. Okay? It is by far the most important thing you have to realize. Since the net force is 0, all of the forces cancel each other out. The forces up the ramp and the forces down the ramp. So, I know I have 200 newtons up the ramp. I have to have 200 newtons down the ramp. How big is friction? 30 newtons. Okay? How did I figure that out? Right. Okay? I know I have 200 up. I have to have 200 down. 170 of it is F parallel. That means force of friction's got to be another 30 newtons. Okay? What was the toughest calculation in that question? Yeah, calculating F parallel. That's probably the trickiest calculation. Other than that, it was all intuitive. Right? I mean, I didn't even write down. This was 0, so that was easy. Okay? Anything times 0 is 0. And then I did vector sum of all forces, 200 minus 170. Okay? Nothing mathematically challenging about that question. Okay? It's intuitively challenging. Like so many of the ones we're going to do. It's intuitively challenging. Okay. Thing to remember. All inclined planes have this triangle inside. Force of gravity is the hypotenuse, F parallel is the opposite side, angle is the same as the ramp. Okay, I want you guys to try this one on your own. Okay, child is sliding down a 25-degree hill on a sled. Friction is resisting with a force of 150 newtons. Child's mass is 50 kilograms. What is their acceleration? This was on a unit exam 2 years ago. All right, so in this one, it's kind of like the first one we did. So the kid is sliding down a 25-degree slide. Okay, or hill. Okay, 25-degree hill on a sled. Their mass is 50 kilograms. Okay. Friction is resisting. Which way is friction going if they're sliding down? Up. Okay. Right, so friction's acting up the ramp with 150. What's pulling them down the ramp? Parallel force. Right. Right. Those are the two forces contributing to the movement of the kid. I still need to calculate F parallel, and I can do that because they told me the mass. So I can go back to my indispensable inclined plane triangle. Right? Force of gravity here is going to be 490.5 newtons. I'm going to have normal force over here, but I won't need it for this question. And then that'll mean that this side here is F parallel, as it always is, and this angle is 25 degrees. Right? So I'm looking for the opposite side. I know the angle and the hypotenuse. So F parallel will be the sine of 25 degrees times 490.5 newtons. Alright, so sine of 25 times 490.5. Alright, so force parallel is 207.29 newtons. Okay, what can I do now? I can find what? Yep, I can find the net force now using the vector sum of all forces. F net is going to be F parallel plus the force of friction. Why am I not using the force of gravity in my sum of all forces calculation? well, it actually doesn't cancel out with force normal, but when I calculated F parallel, it was already the vector sum of these two forces, okay? Or more simplistically, this thing's not going that way, okay? It's not going straight down. Gravity has no part to play here, okay? F parallel is pulling down the ramp, friction's acting up the ramp, okay? All right, so I'm gonna have my 207.29 plus negative 150, okay? Or minus 150, they're opposite. Okay, so we're looking at a net force of 57.29 newtons. What do I do next? Mass times acceleration, right? F net equals m times a. But I'm looking for a, so that'll be 57.29 divided by 50 kilograms. So we're looking at just over 1.1, because we only have two significant digits here. So 1.1 meters per second squared. What's my direction? Downhill. Is that different than down? Yes, keep that in mind. Very common mistake, people lose a mark on it. They say that on a question like this, the vector is down. That means they're falling through the hill. Okay? They're not doing that. They're going downhill. Down slope, down ramp, 25 degrees above vertical, something other than down, okay, because it's not down. All right, is that making a bit of sense? It takes a little while, but the big thing is know this triangle. Know the internal triangle, that's what you need to do here. All right, now, different kind. This one's just about vectors. All right, I want you guys to try this one. So we've got two vectors, two forces pulling this box on a frictionless horizontal surface. Right? I want you guys to calculate the acceleration of the 50 kilogram box. Okay, first thing, draw a free body diagram of the situation. So we've got our 50 kilogram box. Right? This is going to be due east, which is what both of my forces are measured from. Right? So I've got a 35 degrees north of east force, that's 150 newtons. And then I've got a 10 degrees south of east, and it's 115 newtons. All right, that's my free body diagram. Other than identifying the forces, it doesn't help me very much. Okay, what do I have to draw next? A vector addition diagram, right, tail to head. I mean, which direction is this thing going to go? Well, probably not due east, right? There's more force on this one, which is angled more north than this one is. So it's probably going to go a little bit north of east, all right? But if I draw a vector diagram, I'll know for sure. So I'm going to draw my first triangle. So we'll say that's 30 degrees, okay? And it's 150 newtons. Here's X, here's Y. And then my second force, okay, is 115 newtons, and it's 10 degrees south of east. Okay, so we've got an X and a Y here. All right, that means that my net force is my result, this line. All right, and this would be its Y component, and this will be its X component. So no different than adding two displacement vectors together. All vector quantities are added in the same way. Okay. You okay, Sydney? Oh. It's okay. This one's not for marks. Okay. All right. First thing we got to do is calculate what X is. All right. X is the adjacent side to the 30-degree angle, so that'll be cos of 30 times 150 newtons. All right, so that side's 129.9 newtons, and I'm going to keep all the decimals in my calculator. All right, Y is going to be the sine of 30 degrees times 150 newtons, so that side will be 75 newtons. So this is east, this one is north. Right, for my directions. For the red triangle, red x is the adjacent side, so we'll have the cos of 10 degrees times 115 newtons. All right, so that side's 113.25. And it's east. And then y is the opposite side, so it'll be the sine of 10 degrees times 115 newtons. Okay, and then it's 19.97 newtons. And that's south. All right, what do we do next?
It's 35. Yeah, I think 35.
Oh, it's 35. You guys point that out after I get it all done?
That's what
No, just let Coder, who didn't sleep very well last night, just let him make an ass of himself. Record it and put it on YouTube later for everyone to laugh at. I know where we stand. Goes to 35 times 150. Hurts my feelings. Alright, let's try that again. Alright, cos of 35 times 150. 122.87, is that better?
No.
Well, it has to be better.
But it's not.
But it is. Cos of 35 times 150, right? Yeah. Okay, and then sine of 35 times 150. 86.04. Okay, and that one's north. Okay, now what do? Now we find our resultants, x and y. So green x and green y. Okay, that's our next step. So green x, both of them are east, so that's easy. We just have to add them together. Okay, so that'll be 113.25 and 122. All right, so our total green x is 236.13. Newtons east, okay, and green y. Do I add or subtract them? This time I subtract because one's north and one's south. All right, so that'll be our 19 and our 86. Whoop. That one minus that one. 66.07 newtons, and that is north. Okay, now that I've got the two sides of that triangle, now I can calculate the magnitude of my net force. All right, so it'll be the 236 squared plus 66 squared, obviously with all the decimals in it. All right, so we're looking at 245.19. 0.19 newtons, and then we have to get the direction. So looking at my triangle here, this is the angle I want to find. It's going to be north of east, but I'll use y and x to get it. They're the opposite and adjacent sides. So 10 to the minus 1 of the opposite side, which was 66, over the adjacent side, which was 236, will give me theta. All right, so we're looking at 15.63 degrees. north of east. Of course, you could have had the complementary angle as well. All right, so now I've got the net force and the direction. Okay, am I done? No, I still have to find the acceleration. All right, so I'm going to continue on here and say that acceleration equals F net divided by m. So all of that was to do vector sum of all forces. Sometimes it's a lot of work to do vector sum of all forces, especially if there are a lot of vectors. Right? You won't get that many where there's that many vectors. Right? We got 245.19 divided by 50 kilograms. Okay, so our acceleration is going to be, I think we only have two significant digits there, so 4.9 meters per second squared at 16 degrees north of east. Okay, and obviously you could have 74 degrees east of north if you drew the triangle the other way. All right, so again, always the same steps, right? That one, yeah, that one was a bit more involved just because you had to do some vector addition, but it's nothing you haven't done before. Okay? It's just applied to something different. Okay, so I think that's all the practice ones I had. Yeah, it is. Okay, so here's what I want you to do. In your digital workbook, and I'll call it up here in just a second, okay, we got up to about 8 or 9 the other day on the first worksheet, and we couldn't go past that because they were inclined planes after that. And I hadn't taught you inclined planes and stuff. So, I want you guys to go back to the digital workbook, and I want you working on some of the problems from there. Tomorrow we're going to be doing a lab, so it won't be like do problems every single day for 2 weeks. We'll break up the monotony a little tomorrow. Okay, so I think we got up to about, no, actually we did even further than that because we did some of those elevator questions. So, I want you guys to start on 18 and go from there. See if we can get all the way to 25. From 18 to 25 today. Alright, so those are all in your digital workbook, and if there's any that give us trouble, then just ask and we'll walk through them together on board. Okay? You may. Alright, we are going to be looking at ones that are a bit more involved than this as we go. Okay, some that will involve vectors and some that are inclined planes and stuff like that. So we still have some other types of problems to cover. I imagine when we get to number 21, there'll be a few questions, so give it a try, but we'll probably walk through that one together. Okay. But I take requests, so any ones that give you trouble, just ask. Okay, so the big thing to realize here is that the only force that's really important that's acting on the car is the force of friction, and that's for this reason. We got 1,500 kilograms worth of mass, right? Okay, so the car is 1,500 kilograms, but it's on a level road. So yes, gravity is acting on it, and so is force normal, but they're what? They cancel each other out. They're equal. So they don't play a part in the vector sum of all forces, because when we add them together, they add up to 0. That means this becomes my net force. Okay? If you have a question where you're on a level road and you slam on the brakes or you run out of gas and roll to a stop, what's stopping you is friction. There aren't any other forces that matter. Okay? The engine is no longer propelling you forward, so the only force present that matters is friction. So friction becomes my net force and has a value of 18,000 newtons. Since I know the force and I know the mass, I can calculate the acceleration. So 18,000 divided by 1,500 gives me 12 meters per second squared. All right, and that's actually going to be negative. Why is that important?
Because the car's going back, or like slowing down, not going fast.
Right, the car is slowing down. If I don't put that in my formula later, when I'm calculating the distance, it makes a difference. All right, so I need to now calculate, okay, my displacement. The other things I have are VF, I come to a stop, VI, 24 meters per second, and I just calculated acceleration, 12 meters per second squared, and it's backwards. So this formula has everything I have and the thing I'm looking for. Could I solve this in more than one step? Yes. Why would I? Okay, I would want to solve this in one step. So D equals VF squared minus VI squared over 2A. So that's going to be 0 squared minus 24 squared divided by 2 times negative 12. All right, 24 squared divided by, or sorry, negative 24 squared divided by negative 24 seems to be 24. Yes? Okay. Here's where the negative is important. If you punch that into your calculator and you don't make the acceleration negative, you get 24 meters backwards. Okay? Now, I realize that you guys would all make that correction in your head. Okay, oh, right. You know, just because I'm on the brakes doesn't mean I'm going backwards. Brakes don't make me go backwards. They make me accelerate backwards, but they can't propel me backwards. All right, making sense? All right, how are we doing with 19? Okay, I'm gonna give you guys a little bit more time then, see how we do here. We'll have our 1.5 times 9.81. Right, so that force is 14.715 newtons. Okay, as we said, there aren't any other forces. The table is frictionless, it's flat, so gravity and normal force balance each other. All right, that 14.715 newtons is the driving force or net force of the entire system. Everybody all right with that idea? Okay, so we just did sum of all forces then. F net equals 14.715 newtons. Can I calculate the acceleration of the box? Okay, how do I do that? It doesn't specify which box. Does it have to?
No.
Actually, it does. It should say the 1.5 or the 1.0 for this reason. Their vectors are different. Their magnitudes are the same. Okay, the magnitude of the acceleration of each box is the same, but it doesn't. It should specify. Okay, which box so I could give a vector. In this case, it should say what's the acceleration of the system because it doesn't tell me which box to calculate it for. All right, so acceleration will be my F net, 14.715 newtons, divided by how much mass? 2.5, right? The whole system is being accelerated here. And that's the thing we have to remember about this, okay? Is that the whole system is being accelerated. So that'll give us our 5.9 meters per second squared, okay? For the system, it would be to the right for the 1 kilogram mass and down for the 1.5 kilogram mass.
How do we start off 21?
Okay, so 21 is an elevator question. When you're standing in an elevator, if you probably all, whoa, person has a really long neck. If you stand on a bathroom scale, what does it tell you? Get off, get off! No, it doesn't say that. Okay, it tells you your what?
Mass.
It tells you your mass. We all say it's our weight, but we know better. Okay, this scale actually tells me my weight. But if you've ever ridden in an elevator, you know that you feel lighter and heavier depending on which direction you're going. Okay? In this elevator, as the elevator begins to accelerate upwards, the scale reads 775 newtons. What the scale is showing is how hard the floor is pushing up on the person. Okay? So that's reading then the upwards force. the upwards force is 775 newtons. What's the downward force? 725 newtons. Okay? This is what we call apparent weight and actual weight. Okay? This is your actual weight, 725 newtons. But you can feel lighter or heavier than that depending on the situation. Right? If we're accelerating downwards, our apparent weight will be less than 725. If we're accelerating upwards, it'll be more than 725. All right? Okay, so if you're working on 20, okay, remember that the way that 20 sets up is it's actually a pulley like this, where we have a 2.0 kilogram mass and a 1.5 kilogram mass. Okay, obviously they're both going to have a force of gravity that is acting on them. Okay, so this one here is the 14.715 newtons. This one's the 19.62. Okay, so that's why we simplify the diagram to look like that. The net force is pulling on 3.5 kilograms of mass. Okay, and then for 21, right, the one thing that you have to find to solve 21 is the mass of the person. Well, remember that force of gravity, which we know is 725 newtons, equals mass times the acceleration due to gravity, which we already know is 9.81. So we should be able to calculate the mass. You need that to get the acceleration. 22, okay. All right, so an object's being pulled vertically upward by a rope. Tension in the rope is 95 newtons. Okay, and it's an 8 kilogram object. All right, what other force is acting here? Right. So you got to calculate that, then you got your net force. This minus that. Yeah? All right, so you will have a quiz tomorrow, guys. I'll be posting it here after school.